Birch Aquarium at Scripps Institution of Oceanography at UC San Diego's Jeffrey B. Graham Perspectives on Ocean Science Lecture Series. My name is Caitlin Scully, and I'm a Scripps Oceanography graduate and a science communicator at Birch Aquarium. Today is our first talk in a new climate-focused mini-series that is dedicated to Scripps Oceanography's multifaceted work on our changing planet. Scripps Oceanography researchers are tackling the tough questions about the impacts of climate change on oceans, ocean ecosystems, and global society, as well as determining how science can best inform climate change solutions. Today, we are delighted to welcome Dr. Yassir Eddebbar for his presentation titled Oceans Out of Breath: Oxygen Minimum Zones in a Warming Climate. Yassir is a postdoctoral scholar at the Center for Climate Change Impacts and Adaptation at Scripps Institution of Oceanography. He also received his PhD in oceanography at Scripps, where he works to understand the coupling of oceanic oxygen and carbon cycles to Earth's climate when he was an NSF Graduate Research Program Fellow in the Atmospheric Oxygen Lab. Currently, as a member of Scripps' Integrative Oceanography Division, he's focused on improving our understanding of how changes in climate and ocean circulation patterns impact marine ecosystem habitats on the regional scale, with a particular focus on the oxygen minimum zones of the tropical Pacific. As a previous NSF Interdisciplinary Graduate Education and Research Training Fellow, Yassir has been involved in efforts to communicate the central role of the oceans to climate policy and to society in general. He enjoys engaging with policymakers, teachers, and the general public on a variety of ocean and climate science related topics. We are so happy to welcome Yassir. Thank you for speaking with us today.
Thank you so much, Caitlin, for having me. Thanks.
Yeah, great. So we're really excited that we're able to kick off our second Perspectives lecture of this new virtual series. So just so everybody knows, before we get into the questions, this is more of a Q&A style compared to our more traditional Perspectives lectures. And we are going to be taking questions from the audience at the very end. And if you're signed in on Facebook, you are able to submit those questions via Facebook. And if you're on YouTube and you're signed in, you're able to submit those questions on YouTube as well. All right, Yassir, are you ready for the first question?
Let's do it.
All right, so can you tell us, why is oxygen in the ocean important to study? And can you tell us what's so special about it?
Sure. But first off, thanks again for having me. I'm really honored to be part of this lecture series, Caitlin and the rest of the team. Oxygen is really fascinating and it's really special for a variety of reasons. One of the main reasons we study it is that it's really important for life in the ocean. Without oxygen, there's simply no life in the ocean, just like there's no life on land without oxygen in the atmosphere. One of the key things to know offhand about the distribution of oxygen in the ocean is that there's way less oxygen in the ocean's interior than there is in the atmosphere. So there's about 37,500 petamole of oxygen in the atmosphere, so about 20% of the atmosphere is filled with oxygen. Whereas there's only about 227 petamole, so there's way less oxygen in the ocean. So that means that marine organisms have to work really hard to get that oxygen. For example, if you're a rabbit or a cat, you need to breathe about 3.6 liters of air to get 1 gram of oxygen. Whereas if you're a shark or a fish, you need to get about 156 kilograms of water or 150 liters of water through you before you can get the same amount of oxygen. So it's really hard to breathe. It's not as abundant. And there are values of oxygen that are detrimental to fish health, and they exist throughout the ocean's interior, in certain parts of the Pacific, for example. And these are called hypoxic conditions. These are values of oxygen that where when they reach about 60 micromole per liter or less, marine organisms start to feel severe physiological changes. It's like humans without air. And that's going to depend on whether you're a crustacean, like a crab, or a fish, or a bivalve, or a gastropod. And you could see here in the plot to the left, to my left, you see that right around 60 micromole per liter is that hypoxic depth below which many organisms begin to feel this hypoxic conditions. So throughout the oceans, marine life is going to avoid this hypoxic condition, and that's going to set up their marine ecosystem habitat. So So how much of marine organisms can survive below or above? You could see up here, this figure shows in green the fraction of species of mollusks, or in orange, the fraction of species of fish, or in blue here, the fraction of species of crustaceans that can live below the 60 micromole or the hypoxic boundary that we picked here. And you can see that it's about less than 50 or 40 or 60% of species can live in those thresholds. There's other thresholds that oceanographers use, like suboxia, and this is where oxygen gets really close to zero, but not necessarily zero. And at that threshold, microbes begin to conduct various biogeochemical reactions that drive various changes in the nutrient cycle. We'll talk about that in a little bit. And then finally, last terminology that I want to define is anoxia. This is when there's no oxygen, and that's also possible to be found in the ocean's interior. So we've, for many of you who are reaching us from San Diego, you've probably remembered the beautiful bioluminescence that came about in late April and mid-late April, and then started to go away in the first couple of weeks of May. And if you live by the ocean, you would smell that stagnant smell of organic matter decomposing. And one consequence of these red tide is hypoxia. They induce hypoxic events along our coast. And there's a really great lecture by Michael Latz from this series that goes into the details of what red tides are. You could see here in this time series by Clements and Smith that oxygen levels have dropped to nearly anoxic and also very hypoxic conditions. And we've seen some fish kills occasionally here along our coast that accompanied these hypoxic events. And that's really why we study oxygen, because oxygen can go down to nearly lethal conditions and without any warning. And that can happen, for example, from coastal hypoxic events, for example, from the red tides, also seen here in St. Helena Bay in South Africa, from upwelling-driven events, for example, here off the coast of Goa, India, and also from anthropogenic activities like nitrogen deposition from wastewater treatment plant, for example, shown here from a treatment plant off the coast of Rhode Island. But what we're going to talk about today is not coastal hypoxia, but we're going to talk about hypoxia in the open ocean. And to show just why we want to understand how oxygen differs, both in the ocean's interior, throughout the open ocean, I've picked this really nice paper by Lothar Strom and colleagues, where they tagged some blue marlins, and they followed them as they got out of the oxygen minimum zone off the coast of West Africa here. So you can see the white line is the trajectory of the first blue marlin, and it just stays in the upper 100 meters as it's over the low oxygen minimum zone of West Africa. And then as soon as it leaves, it begins to go up and down, all the way from the surface down to about 500 meters, and it's able to forage without any restrictions. The other blue marlin, which stays in the oxygen minimum zone, stays largely in the upper 100 meter to 200 meters. So it's not able to go below that level of 2, which is hypoxic, and it doesn't allow it to metabolize as well. So that's really why we study oxygen in the ocean. It's extremely important to marine organism, and we want to know why does it look the way it does in the ocean, what causes its distribution, and how it's going to change in the future.
That's really fascinating. I know on the land we have lots of oxygen, and we don't really think about how oxygen levels can change in different parts of the ocean. So it's really a neat way to think about a world that's very different from ours, but also so connected. Now, Yassir, you talked about oxygen minimum zones. Can you talk to us a little bit more? What are oxygen minimum zones, or OMZs, and where do they exist, and what causes them?
Sure. So first off, I think we have to make, again, the distinction between oxygen minimum zones and coastal hypoxia. So oxygen minimum zones is what you see here in blue. These are large, open open ocean, big areas of oxygen minimum that occur naturally, and we'll talk about what's driving them, whereas hypoxic coastal regions are constrained to the coastline, and they're typically either driven by natural phenomena like red tides, but also anthropogenic effects like the delivery of nutrients from wastewater treatment plants or agricultural activities. So it's really important that we separate these two phenomena because they get confused a lot in the public's mind. So the first one, coastal hypoxia, or you've probably heard of them as dead zones. They result from this process called eutrophication. So say there's an agricultural field or large-scale industrial processes along the coast, for example, off the east coast of the United States, and there's a massive rain event, and that rain event drags all the nutrients, nitrogen, and all the pollutants out offshore. That fertilizes the upper ocean. And all that fertilized phytoplankton that grows ends up deposed in the ocean's interior along the coast and decomposes. And as it's decomposing, microbial organisms remove oxygen, and we end up with these oxygen dead zones along the coast. The oxygen minimum zones that we find, for example, here off the tropical Pacific, these are related to microbial consumption and production from the open ocean, but they're also associated with the large-scale circulation of the ocean. There's a component which we call ventilation, how much water circulation is happening in that region. So where can we find oxygen minimum zones? So we can find the biggest ones, for example, off the northern tropical Pacific. So that's one of the biggest oxygen minimum zones, and you can see it here with values below 60 millimole per meter cube. There's also another one south of it. This is the South Tropical Pacific, OMZ. And then in the northern tropical Pacific, there's another one called the North Tropical Pacific, OMZ. And then off the coast of India, in the Indian Ocean, the Arabian Sea, there's a very intense oxygen minimum zones that extends pretty far south. And then finally in the Atlantic, there's a couple other oxygen minimum zones, but they're fairly weak. And that's, as we're going to see, because there's a lot of ventilation in the Atlantic. So these oxygen minimum zones are really fascinating. They have very different character. Each one differs. So there's, for example, a lot of variability between them just in the depth. So if you go to the tropical Pacific OMZs, you're going to reach hypoxic depth at about 50 to 100 meter depth. So off the coast of Costa Rica or Mexico, if you were to go offshore, you can find an oxygen minimum zone there just in the upper 100 meters. Whereas the oxygen minimum zones of the Atlantic are going to be deeper, and you're also going to see much deeper oxygen minimum zone in the northern Pacific. That reflects, again, this process of ventilation. So why are the oxygen minimum zones where they are, and what determines their distribution? The first process is really simple. It's just that warmer water holds less gas. And this graph here shows as temperature increases, oxygen solubility in seawater decreases. And you can actually see this in the upper distribution of oxygen at the surface. So we know that the low latitudes are usually warmer. They receive more sunlight than the high latitudes. And as a result, there's less oxygen at the surface in low latitude versus the high latitudes. So that's the number one process at the surface that's operating in the mixed layer. Also, there's a lot of exchange between the mixed layer, the upper part of the ocean, and the atmosphere at all times between these two elements. And so whenever there's an undersaturation or less oxygen at the surface, the mixed layer is able to absorb that oxygen right away from the atmosphere. However, if you go down to 200 meter depth, you're going to see a slightly different pattern. You're going to see this pattern where there's low oxygen along the eastern part of the basins, here off the Pacific and the Atlantic and the Indian Ocean. And that's not necessarily related to the distribution in temperature. So that's where the effects of circulation and biology and chemistry come into play. So in the open ocean, there's what we call the subtropical gyre. Many of you are familiar with the subtropical gyre through the Great Pacific Garbage Patch, for instance. And what you'll notice is that the subtropical Pacific gyre, in its anticyclonic flow, essentially misses the eastern part of the Pacific. So that's what we call the shadow zones. So there's just not enough ventilation, not enough oxygen that reaches that part of the ocean. And the other part of this process is biology and chemistry. What you notice is that along the equator, there's a lot of upwelling. There's a lot of biological activity and phytoplankton at the surface. That phytoplankton, again, sinks, similar to what we see here with coastal hypoxic events. And as it's sinking, microbes are able to respire all that organic matter. So they remove oxygen and they remineralize it into CO2 and nutrients. And so the balance of oxygen is essentially this balance between circulation and biology at depth, with some contributions from temperature, but at the surface, it's mostly temperature. So, and just to sort of visualize this a little bit more, here's a distribution of oxygen at 150 meter depth. And you can again see the oxygen minimum zones in red. And when I superimposed this, the subtropical gyre circulation, you could see that they essentially, the regions where they are not reaching the basin is where you're going to find these low oxygen minimum zones. If you were to take a transect right through the Pacific and the Atlantic, you're going to see differences in that ventilation. You'll also see differences in how much oxygen reaches the ocean's interior because of what we call the overturning circulation. And that's really important to try to understand differences between the Pacific and the Atlantic, for example. The Pacific has much bigger oxygen minimum zones, largely because there's not enough overturning circulation, not enough deep water that forms in the North Pacific and ventilates the ocean's interior. Whereas the Atlantic, there's a lot of oxygen ventilation from North Atlantic deep waters. So this is water that forms here off the coast of Greenland in Canada and descends, and on its descent, it ventilates the rest of the interior. So think of the oxygen minimum zones as your basement at home. And the high latitude and mid latitudes are the windows to your home. So because the basement is so far away from these windows, they don't get enough circulation and they're going to feel stagnant and the air there is going to feel old. And so the same way that ventilation occurs in your home, it's essentially the same process here in the ocean. There's just not enough ventilation reaching that area. But there's other processes. For example, the oxygen minimum zone of our coast here in the California current region is driven in part by upwelling. So during spring, for example, you notice that there's more winds coming from the northwest. And those winds are driven in part by the temperature difference between land and ocean. Land just warms much faster than the ocean. That creates a gradient in pressure, and it creates winds that go towards the equator. And those winds push water, not with them towards the equator, but to 90 degrees to the right. And that's because the Earth rotates. And so as those waters are being pushed offshore, upwelling brings up low oxygen water that comes up to the surface, and it's filled with nutrients, and that's going to fertilize the surface. For example, here, as we could see, low dissolved oxygen, high carbon water that's rich in nutrients comes up to the surface and fertilizes the surface. And then again, as that phytoplankton bloom begins to die and descend into the ocean's interior, microbes begin to respire. And that's really sort of what's driving the existence of the oxygen minimum zones. And we can go more and more about all the details of the oxygen minimum zone. I think that's what I find really fascinating about these phenomena, is that the more you dive in, the more you realize that they're extremely fascinating, extremely complex with all kinds of feedbacks. And this is one example. Here's some of the processes from the most recent literature that shows the oxygen zone, for example, off the northern eastern tropical Pacific. It includes contributions from ocean circulation. And within the oxygen zone itself, there's a variety of microbial processes that remove nutrients or recycle nutrients. For example, the process of denitrification, which occurs when oxygen is much lower, and it creates nitrous oxide, which is a byproduct of this reaction and a very powerful greenhouse gas. So these are just examples of some of the chemical and biological processes that are happening in the oxygen mineral zones. In summary, the complexity is really what's fascinating a lot of scientists who want to learn more, but also to try to understand what's going to happen to their future. And just to wrap up here on that question, I think since this is a Birch Aquarium lecture, I want to sort of reference the long history that Scripps has had in studying oxygen over the last 60 or 70 years. For example, the director of Scripps back in the 1940s, Harold Sparrowdrop, wrote one of the first papers that explained why there's an oxygen minima in the ocean's interior and why there's a maxima. And he was the first to say that biology and chemistry have a major role to play in shaping oxygen in the ocean's interior. There was a major other contribution from a researcher back in the 60s at Scripps, Klaus Wurtke, who highlighted the role of ocean circulation and how this sort of weaker horizontal circulation and more vertical circulation controls the oxygen distribution in the upper ocean. And then really, it wasn't until various cruise sections that detailed the distribution of oxygen in the ocean's interior by people like Professor Lynn Talley, that we've really got a better understanding of just how complex this three-dimensional structure of oxygen is in the ocean. And then later on, as more cruises have begun to look at the organisms looking inside of them, for example, many of the research done by Professor Lisa Levin has looked at the communities that are living within these oxygen zones and how they adapt to such low oxygen values. And then finally, a major contribution to the field came from Dr. Ralph Keeling, who not only measured oxygen in the atmosphere for the first time, but also has done a lot of work in showing how oxygen minimum zones are going to respond to global warming as the anthropogenic CO2 emissions in the atmosphere keep on building up. So I just wanted to give sort of an overview of the incredible role that oceanographers and atmospheric scientists at Scripps have done, and I'm really honored to also be mentored by many of these people. So we owe them a great deal of appreciation.
That's really amazing. And thank you for sharing all of the work done by colleagues and those before you at Scripps. I think it really does show and highlight how studying something that might seem as simple as how much oxygen is in the ocean is really a multidisciplinary and a very complex question to answer for not just one oceanographer, but it takes many, many different scientists from many different fields. So looking at what you just said, those oxygen minimum zones for the average eye might seem really large, but it was amazing to hear how all those planet-wide influences impact their size and their location. Now, with some challenges coming to us with global warming, do you think it's going to affect the global oceanic oxygen? How will these giant oxygen minimum zones respond to more warming that we see in our future?
It's a really good question. And maybe to start off, it's important to just sort of take a step back and see how much the ocean has done in terms of mitigating climate change. So because of the buildup of greenhouse gases in the atmosphere, most of the heat trapped by greenhouse gas emissions have gone mostly into the ocean. That's because the ocean is large, it's very deep, it's very dynamic, so it circulates, it's able to take that heat and put it in its interior. And very importantly, it's got a large heat capacity. It's able to absorb a lot of heat for very little temperature change. And you can see it here in the panel to the left. You can see the amount of energy that's trapped in different parts of the planetary system. And you can see that the atmosphere, land, and ice only account for a small portion of the energy trapped by the greenhouse gas emissions, whereas most of the heat is trapped by the ocean. And a lot of it has gone into the upper ocean. So this is the upper 1,000 meter. And you can see it in the distribution of ocean heat that's recorded in temperatures over the last 6 decades, that the North Atlantic, North Pacific, and the Southern Ocean have warmed the most. And that's because, again, they're the windows into the ocean's interior. And as the atmosphere is warming up and most of that heat is going into the ocean, it's going to go into the ocean through this mid and high latitude region of ventilation. So we're going to hear more about this from Professor Sarah Gilly next. I'm really excited to hear about that. What we are interested in is how this warming impacts oxygen. So in the last 5 or 6 decades, as the ocean heat content have gone up in the upper 1,000 meter, we've noticed in the observations that the oxygen content globally has decreased. And that's the rate at which it decreased is about 2% of the total oxygen inventory. That might not seem like a lot, but 2% is a lot, especially for regions where oxygen is already low. And you can see that in the distribution of the oxygen loss that we've recorded, that a lot of it is in regions, for example, here in the tropical Pacific, where oxygen is already low. So a decline in oxygen in these regions where oxygen is already naturally low can have a really big impact on where that hypoxic depth sits. You can also see there's a lot of changes in the Arctic, in the Southern Ocean, and in the South Atlantic. And so when we say 2% decline in total oxygen in the ocean, that's really the global mean. It doesn't say much about the regional changes. And this paper by Professor Lisa Levin really highlights that, where we can see, for example, especially in the North Pacific, that the tropics have account for about 40% of that change, the tropic and the North Pacific. In certain areas like the Southern California Bight, just offshore from here, there's been a 21% decline in oxygen from 1984 to 2006 at depth of about 300 meters. In Monterey Bay, we've seen declines of about 40%. In Station Papa, which is one of the longest time series recording oxygen, there's been a 20% decline in oxygen. So there's some pretty large changes regionally that are superimposed on sort of a smaller decline globally. But there's also a lot of uncertainties in some of these numbers. For example, in the tropics, the observations can be sparse. And so there's still a lot of work going into figuring out how robust are some of these trends and how much more observation we can get out of new methods. The main mechanism by which oxygen is being lost because of warming, one, we've said earlier that a warmer ocean can hold less gas, and that's the gas solubility component of the equation. That's just thermodynamics, but that only accounts for about 15 to about 50% of the change. A lot of the change is going to happen because of the circulation effects and the biology effects. And this is an illustration. It looks pretty complex with all kinds of arrows, but essentially if you follow these arrows, these, for example, here are the mid-latitude and the high latitude, whereby water goes into the ocean's interior. And so as the ocean warms, the upper ocean becomes more stratified, becomes harder to mix waters between these different isopycnals or different layers of same density. And the upper ocean becomes more stratified, there's less ventilation into the ocean's interior, so that kind of creates even more time for these microbes to respire oxygen and less oxygen supply to the ocean's interior. So that's one mechanism by which we think that the oxygen minimum zones are going to be expanding as the ocean warms. And we can turn to models like climate models to sort of get a general understanding of how the Earth system is going to respond to this warming. To the right is a combination of different models that were submitted to the IPCC report. And the IPCC report is an intergovernmental panel of experts that provide input from the literature on the latest science. And they use Earth system models to try to infer what's going to happen by the end of 2100. And what these models are showing us is that as the ocean warms, there is going to be less oxygen in the layer that we call the thermocline. So this is the depth of about 200 to 600 meter depth. This is typically where you can find a lot of these oxygen minimum zones. They show that there's less and less oxygen in the high latitudes. For example, here in the Southern Ocean, in the North Pacific, and in the mid latitudes, and the North Atlantic. And that's the rate of the oxygen decline here, shown for the global oxygen content change in percentage. So by 2100, depending on what scenario you pick, if it's low emission scenario in blue, or a high emission scenario, which is business as usual, we're looking at anywhere from an additional 2% to 4% change in the oceanic oxygen inventory. So the amount of oxygen that might be lost in the future depends on how much greenhouse gas emission we emit in the future. Well, one interesting thing that I want to point your eyes to is this region in the low latitudes. So we'll talk about that in a bit, but the models don't really agree very much on what's going to happen in the low latitudes. And the agreement between the models is shown here in dots. So where there's a lot of agreement between the models, you'll see dots, and you'll also see a decrease in oxygen. Whereas in the low latitudes, there is generally low disagreement between the models, and some of them even show that there's going to be an increase in oxygen in these oxygen minimum zones. So the picture that the models are giving us is really complex. But models are just models, and so we have to use them with a certain amount of caution. We also have to root our understanding of the Earth system in observation first, but get some information from the models. Then I just want to sort of point out that the oxygen changes that I've shown in these models are just one of many other impacts that we expect from a warming planet. We know that the Earth system is going to warm up, and the sea surface temperature and the ocean's interior are going to warm. So there's a lot of agreement between models on that warming. We also know that the additional CO2 in the atmosphere is going to cause more acidification or a decrease in pH. And that's also pretty well understood. A lot of it is driven by carbonate chemistry. That's really well understood. And then finally, we also think that there's going to be changes in primary productivity. So the amount of nutrients that come up to the surface and the amount of productivity from phytoplankton bloom might change. That's going to depend on circulation and warming and variety of different processes, but that's even less certain than what's happening with oxygen. But I just want to sort of show that there's way more than just one impact, and oxygen is just one of them, but it's also one of the most important ones. And we have to study it sort of in concert with these other impacts. And as a scientist, I'm really fascinated in this topic from a scientific standpoint, but I'm also concerned about its impact on marine ecosystems. Marine ecosystems are really complex, and especially the interaction between different communities vertically and also laterally. And so as the ocean warms, not only is the oxygen supply or the oxygen in the ocean's water is going to decrease, the oxygen demand from fish is also going to increase because it's warmer. And as these OMZs are expanding, these marine ecosystems are going to get squashed further up. So that the hypoxic depth, as it shoals, is going to create less space for these different marine ecosystems to coexist. So that means that preys are going to become more vulnerable to predators. Fish, as a general, is going to be more vulnerable to fisheries. A lot of this is work in progress, and we're really just starting to understand the impacts of changes in oxygen on not only ecosystem dynamics, but also marine organism health, including vision. And we're going to hopefully hear soon within this lecture series on some of the biological impacts of these oxygen minimum zone expansion. And here's an example, really a cool example that shows, for example, here off the coast, as the oxygen minimum zone shoals, we expect that there's going to be decoupling or changes in decoupling between pelagic organisms, those that live offshore versus those that live on the benthos, on the ocean's floor. So there's a lot of exciting work that's happening that's trying to understand how marine ecosystems are going to adapt or react to these changes in the ocean's environment. If you want to learn more, there's some great resources. One is the most recent Ocean Cryosphere report that's been done by the IPCC. And there, they've assembled a lot of the most recent literature on what's happening in our oceans, including oxygen. It's got a very thorough section on oxygen. And if you want to get into even more detail, the International Union for the Conservation of Nature has published a report recently, and Scripps scientists and scientists from around the world have contributed to sort of summarizing a lot of these scientific problems in this report, and I strongly recommend to look it up online and get caught up with the science behind it and also the implications for marine ecosystems that we expect from this problem. So.
That's really fascinating, and it's really great that Scripps Oceanography and UC San Diego have been advocating so much recently to make sure that the oceans are included in these larger global climate conversations that we're having, since the ocean is such a driver for so many of the climate change impacts that we see today. Now, Yassir, you touched on this a little bit, but I was wondering if you could tell us what are some of the biggest challenges when it comes to studying these oxygen minimum zones, or these OMZs, and how well are we able to actually observe the oxygen in the ocean, and how does that relate to what the climate models are telling us?
Yeah, sure. The best part about doing science are the challenges. And that's really where we derive a lot of our curiosity and a lot of our motivation, is to try to find these problems that are tough. And oxygen is really tough because it includes a bunch of different processes happening at once. So ocean circulation, chemistry, biology. And it's also a problem that we don't fully understand yet. The science behind it is still somewhat young. And you can see that, for example, in this discrepancy between what the observations are showing and what the models are showing. I've sort of referred to earlier that the observations are showing a substantial amount of oxygen loss in the tropics, whereas the models mostly show very little changes and even a positive increase in oxygen. So this discrepancy between the models and observations in terms of what oxygen should do has really motivated a lot of new insights into why is oxygen declining in the tropical Pacific. And one of the ideas that is also really prominent in the literature is, what is the role of natural variability? For example, here to the left, I'm showing sea surface temperatures that are associated with natural variability phenomena we call Pacific decadal oscillations. And it's just an index that we use to describe decades that are typically cold, for example, the 1960s through 1970s, and decades that are warm, for example, the 1970s through the 1990s. And these natural modes of variability, like the Pacific decadal oscillation, El Nino, that many of you are familiar with, they induce a lot of variability, not only in temperature, but also in the biology and the chemistry of the ocean. So what that does is it really creates a problem in trying to identify what is human-driven, what is the change in the oxygen that's driven by human warming, and what's natural. And that's something that really fascinates me and many of my colleagues, but it also makes it really hard to detect the anthropogenic signals in the ocean. And to the right here, I'm showing what we call the time of emergence, which is really the time by which the anthropogenic signal or the anthropogenic impacts on oxygen are going to be detected in measurements. And sometimes we might not be able to find that for another 50 or 100 years, for example, over regions in the tropical Pacific, but in other places, like in the northern tropical Pacific, in the Atlantic or Southern Ocean, this paper here shows that we can expect to see the influence of human warming on oxygen in the next 10 years, or even now, or even the next 20 or 30 years. So natural variability is really important. It's one of the biggest challenges that we face. Another problem is that the models themselves don't do so well in the tropics. When you look at their projections here for regions that are hypoxic, below, say, 50 millimole per meter cube, the behavior of different models, and different colors here show different trajectory for a different model. Some models show that the volume of the hypoxic or the oxygen minimum zone is going to increase in certain models, sometimes really increase. And for other models, it shows very little change, if not a decrease in the volume of the oxygen minimum zone, or increase in the oxygen content in that region. So each model is going to show a different future in that region, in part because of their biases. And the model biases here, what I mean by bias is that they're not reproducing the mean state or the processes in that region well. So how does that change, for example, from one generation of model to the next? What I've shown here is models from the last IPCC report. And so there's been a lot of work over the last 7 to 10 years to try to improve how these models represent ocean circulation processes. But the most recent paper, this just came out last week, shows that models are still doing pretty poorly in that region, and they're also still disagreeing on what's going to happen in the tropical Pacific. So a big challenge is try to understand what's happening in the tropical Pacific. How can we better model the oxygen minimum zones in that region? And one big challenge there has been computational resources. In order to represent the oxygen minimum zones, we have to get really small-scale circulation features right. For example, eddies or equatorial currents, like the equatorial undercurrents. And we have a really good understanding of global ocean circulation in these climate models, but at regional scales, we're now really starting to understand how these smaller scale features are impacting the oxygen distribution. You could see these beautiful patterns starting to emerge here along the coast of North America, the equatorial undercurrent bringing oxygen to the Eastern Pacific, eddies changing the extent of the oxygen minimum zone. So it's really an interesting time to be a scientist. Another really important advantage of using models that it allows us better process understanding of natural variability. We can run a model without any anthropogenic forcing and just try to understand how El Nino is going to impact the oxygen minimum zone, how the Pacific decadal oscillation might impact an oxygen minimum zone, or even how these small eddies, for example, this observed eddy, which is like a storm that happens in the ocean that traps low oxygen water and transports it, and it's been observed here in the Cape Verde Ocean Observatory, to lead to very low oxygen values for almost a month in that region. So models are really critical in trying to help us understand what's happening and sort of get a better idea of the natural versus the anthropogenic component. And then finally, the observations have been sparse over the last 5 or 6 decades. But there's an exciting new program called Biogeochemical Argo Program, and some of you have heard of this as the Argo Program, where a float goes up and down the ocean's interior and records temperature and salinity and delivers it back to us via satellite. These biogeochemical Argo floats are very similar, except that they also record oxygen through a little sensor that you see here to the left. And they're going to be really instrumental in trying to record how the oxygen minimum zones are going to evolve in the next 10, 20 years. So this is really an exciting new development me and many colleagues can't wait to get our hands on the data and try to start to work with it. So to wrap up, I think this is an exciting time to be a scientist, despite all the challenges of few observations in the past or model limitations. There's now more observations than ever. The models are getting better and better. And that's going to really help us become more prepared to the potential impacts of climate change and also natural climate variability as our community becomes more and more dependent on ocean resources, and especially in small island nations and nations around the Pacific. As each country begins to develop their own adaptation plan, they're going to need more observations and better models to try to figure out how these resources are evolving. And feel free to visit our website at climateadapt.ucsd.edu. This is the website for our Center for Climate Change Impacts and Adaptation, where our focus is try to build preparation through more observations, better models to try to understand how sea level rise is going to evolve in the future and how it's evolving right now, how these marine ecosystem habitats, especially oxygen, temperature, and pH, are evolving, and also human health here on land and in the ocean. So yeah, it's a little plug for our center. Please feel free to visit, and hopefully you can find more information there.
That was great, and it's really exciting to know about that new center at Scripps Institution of Oceanography. I wanted to point out to people, it's easy to forget that we really haven't been studying the ocean in an in-depth way for more than about 50 years or so. So it's understandable that we still have a lot to learn, and the combination of that modeling that Yassir and your team are using, as well as this new fleet of Argo floats that'll be floating around taking these physical observations and chemical observations in the ocean, is going to be a great team essentially to try to figure out what's happening on our human time scale, what's happening in the ocean right now, but also the modeling will help us look at what's happening on that planetary time scale, one much larger than any of our lifetime. It's really, really fascinating. Now we have one more question for Yassir before we wrap up and hop into our Q&A. So just make sure if you guys have any questions, now's a great time to submit those in the comments. All right, so our last question for Yassir is, we want to know a little bit more about you. What drew you to oceanography and science and studying oxygen specifically at Scripps Institution of Oceanography? And do you have a favorite thing about studying the ocean and climate?
Yeah, great question. The way I got into science and oceanography is really sort of a circuitous path. I was always near the ocean, always playing around at the beach, either surfing or swimming or diving. And I was always fascinated by just how much changes are happening every single day. The ocean will look totally different from morning to evening, or from one day to the next. The waves change shape. The ocean changes color from day to day, changes sound, and that really fascinated me. And so as I went from high school, where I was becoming more and more interested in science, and on into college, where I attended Orange Coast College, I took a class in oceanography, and for the first time, I was really, really captivated by sort of how I could use my interest in science with my interest in nature, especially the ocean. So I started learning more and more about oceanography and climate sciences. And the more I learned, the more I realized it's really complex. And also it's really important. I've begun to learn that we depend so much on our planet for our well-being. And so studying climate and ocean sciences was sort of the perfect way to both be immersed in this element that I really enjoy, but also sort of try to understand it so that we better protect it. And as a surfer, you're out in the ocean, you sort of notice the changes from day to day, you're more aware of pollution events, for example, after rain runoff events. And so sort of this combination of curiosity about how the ocean works and the climate system works and how the different elements, the ocean, the atmosphere, work, and also what we can do to protect them is pretty unique to climate science and oceanography. So I applied to the best place to do that, and that was Scripps. And I was really lucky to have incredible mentors, like people I've shown earlier in that timeline, Professor Lisa Levin and Dr. Ralph Keeling, and many others who sort of helped me develop scientific curiosity, which is really one of the most important drivers of scientific discovery. Is just trying to figure out how things work and finding solutions to problems along the way. And then I think the second part of your question was, what is my favorite thing about studying ocean and climate? I think it's really the unknown. Not knowing what we're going to find out is my favorite thing about studying ocean and climate science. Oftentimes, when I started my graduate studies, I was on one path and then ended up pursuing very different questions. And while pursuing these different questions, you find different answers than you expect in the first place. That's been really the common and main thing that I enjoy the most about pursuing ocean sciences in general, just the unexpected. The ocean is full of surprises, full of new discoveries, and we're really just kind of putting our toes in, so to speak. There's a lot more that we can learn, and especially a lot more to understand in terms of how it's going to react to our human footprint in terms of pollution or climate change, and also just how it naturally varies and how that impacts us as a society. So I think that's really what I enjoy the most, is the unexpected.
That's really great. And, I have to say, Yassir, that you echoed the same sentiment that we've had many of our scientists highlight. And that's the importance of curiosity, but also flexibility, because you might love one thing, but then find a new and interesting question, and it can take you in a very interesting path. So thank you for mentioning those things. Let's see. Let's dive into a few questions that we have from people. Let's see. We have one here from Jordan, who wants to know, are there times in Earth's past history that are good analogies for what's happening in our ocean today? And can they help inform what we might see in our ocean's future?
Yeah, great question. So oftentimes we look into our past, both in, for example, in cores that we drill from cruises that we take out into the open ocean, and we can infer from changes in, for example, marine organism fossils that are stored in those cores at the bottom of the ocean, what different species have lived, and also how much oxygen was there back then. And one period is the end-Permian period, some couple 100 million years ago, where oxygen was low, and there was a lot of CO2 in the atmosphere apparently from enhanced volcanic activity. And that's one way that we can sort of think about the future, but that's a different analogy. It's an analogy that we can use in terms of what happens when you have these major, big hypoxic events, but the drivers are different. Those occurred over longer periods of time. They had much larger magnitude of warming and oxygen change, but they can still give us an idea about just sort of the impact on marine ecosystems and species diversity, and they're very useful in that regard. So we can use them both as an analogy in terms of what happens when oxygen drops to a very low level, but they're also quite different in terms of the mechanisms that were governing and the magnitude of oxygen change that were happening on those timescales. Great question.
That's excellent. Our next question highlights a little bit of the need for perhaps some ocean and climate optimism. We are wondering, are we too late? Is the anthropogenic measurement, is it too high? Is it too late to kind of turn around where we are with a lot of the changes that we're seeing on these global timescales for our planet?
It's not too late. It's not late. The anthropogenic changes that we're seeing are of great concern, that we can certainly have an impact on our trajectory moving forward. And I think a really big part of having sort of solutions at hand is try to understand the problem more. How much changes have happened because of human versus natural variability? How severe are these changes? And how much do we need to adapt to that's irreversible versus how much is needed to mitigate these changes? And so in terms of optimism, I'm highly optimistic. I've been interacting in the past with policymakers where I've seen sort of change happen over pretty short periods of time, but also I've seen sort of actions taking us in the wrong direction. And that's really a topic for policymakers to do with information and guidance from scientists. But I don't think it's too late. I think there's a lot that we can do, and especially there's a lot that we can learn. And especially in terms of adaptation and mitigation, there's a tremendous amount that science can really bring to the table in sort of learning to adapt and mitigate climate change. Yeah, great question. But I'm very optimistic. I'm very sort of positive about what's going to happen in the future.
I am too, because I know that we have great scientists like you at Scripps Oceanography and at other institutions and research centers around the world who are working so hard to try to learn and understand more about how our planet is changing. And that also brings me to let everybody know that we do have 2 more talks scheduled coming up in the next few months. So our next talk is on August 10th with Dr. Sarah Gilly, who will answer our questions about our warming ocean. And then in September, we're going to be welcoming Dr. Ram Ramanathan to talk about bending the curve. So we'll have a bunch more opportunities to hear about what's happening and also what we can do about it, and hopefully be optimistic about our future. So Yassir, thank you so much for speaking with us today. I really enjoyed your talk, and I know that our guests online enjoyed it as well. If anybody wants to watch it, it'll be available on YouTube forever. So show your friends. And Yassir, thank you so much from all of us at Birch Aquarium at Scripps.
It was my pleasure. Thank you, Caitlin, and thanks everyone for tuning in.
All right, thanks guys, and we'll see you next month. Have a great one. Bye.